Hello and welcome to this online lecture. My name is Patty Kokish and today I'm going to be presenting materials for your online Math 200 class. So today we're going to go through Chapter 5, which is all about probability. We're going to start with Section 5.1, which goes through some of the basic probability rules. So probability you've probably heard of before, and it's just a measure of the likelihood of a random phenomenon or chance behavior. It describes the long-term proportion with which a certain outcome will occur in situations with short-term uncertainty. So for example, if you roll a die, we can predict what will happen in the long run. You'd get half ones, or sorry, 1/6 ones, 1/6 twos, and so on. A coin would have been a good example. You get half heads, half tails. But the outcome in the short term is uncertain. Probability deals with experiments that yield random short-term results or outcomes, yet reveal long-term predictability. The long-term proportion in which a certain outcome is observed is called the probability of that outcome. Now, here is kind of an important rule. This is the law of large numbers, and it says that as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. So as we have larger and larger sample sizes, the proportion is going to get closer and closer to what we would expect. Now, in probability, an experiment is just any process that can be repeated in which the results are not certain. So the sample space, S, of a probability experiment is just a collection of all of the possible outcomes. So it's just a list of everything that could possibly happen. And then an event is any collection of outcomes from a probability experiment. An event can consist of one outcome, more than one outcome. It's going to be denoted just as either the capital letter E, or if there are only one outcome, just a simple event, sometimes we call it, we might denote it with an EI, a little e. So if we consider the following probability experiment, we want to go ahead and identify outcomes, determine sample space, and define an event. So let's consider the probability experiment of having two children. So we want to identify the outcomes of the probability experiment, determine the sample space, and then define the event E, which is equal to have one boy. So the outcomes are going to be that you have a boy and then another boy, a boy and then a girl and then a boy, or a girl and then another girl. So those are the four possible outcomes if you're talking about having two children. So the sample space is going to be the exact same thing. Typically sample space is denoted with a capital letter S, which is not shown here, but then you put in curly brackets kind of your possible outcomes. So you'll see a curly bracket here, and then we've listed in parentheses our possible outcomes. So defining the event of having one boy means that you would either have a boy and then a girl, or a girl and then a boy. So these are subset of the sample space that fit into the event that we want. So they're part of our sample space, but they're what in particular that we're looking for, which in this case is having one boy. Okay, there are some rules for probability, and they are the following. The probability of any event E, P of E, must be greater than or equal to 0 and less than or equal to 1. And then the other thing that has to happen is that if you have multiple different outcomes, the sum of all of the probabilities of all of the outcomes has to equal 1. Okay, so the sum of all of them has to equal 1. Now we have a couple of things to kind of note here. If you have a probability of 1, it basically means that it's a guarantee. It is definitely going to happen. If you have a probability of 0, that means that it's impossible. So for example, if we roll a dice that's 6-sided, an impossible event would be us getting a 7, okay, because there is no 7 on our die. And a certain event, something that would have a probability of 1, would mean that we roll an integer, okay, because all of our numbers 1 through 6 are integers. Now, what a probability model does is it lists all of the possible outcomes of a probability experiment and each outcome's probability. So a probability model has to satisfy the rules from the previous slide. So if we look at this here, in a bag of peanut M&M milk chocolate candies, the colors of the candies can be brown, yellow, red, blue, orange, or green. So we want to suppose that a candy is randomly selected from a bag. We have the table to the right, and this shows the different colors, the different probabilities. And what we want to do is we want to verify that this is a probability model. So in order for it to be a probability model, two things have to be true. Each of the probabilities individually has to be between 0 and 1, which all of these are. If you look at them, they're all between 0 and 1. And then if we add up all of our probabilities, 0.12, 0.15, and so on, it's equal to 1. So this satisfies our second rule. So this is a valid probability model. And then I already talked about this a little bit. If an event is impossible, it means that the probability is 0. So for example, with our M&Ms, the probability that we get a purple peanut M&M milk chocolate candy is going to be 0 because there aren't any. If an event is a certainty, then the probability would be 1. So the probability of us picking a color is going to be 1 because all of these are colors. An unusual event is an event that has a low probability of occurring. Now, this is a little hard to define, but typically we say that if something is less than 5% chance, okay, so if you have a less than 5% chance of something happening, that would be considered unusual. Okay, we have two different approaches. This first one is approximating probabilities using the empirical approach. So the probability of an event E is approximately the number of times event E is observed divided by the number of repetitions of the experiment. So the probability of E is the relative frequency of E, meaning that we take the number of times that E occurs and divide it by the number of trials that are in the experiment. So here we have a Pass the Pigs. It's a Milton Bradley game in which pigs are used as dice. Points are earned based on the way the pigs land. There are 6 possible outcomes when one pig is tossed. A class of 52 students rolled pigs 3,939 times, so a lot of times. The number of times each outcome occurred is recorded in the table at the right. So you'll see side with no dot, that was most frequent, 1,344 times. Leaning Jowler, I'm not totally sure what that is, happened 32 times. So we want to use the results of the experiment to build a probability model for the way the pigs land, estimate the probability that a thrown pig lands on the side with dot, and find out if it would be considered unusual to throw a leaning jowler. So for our probability model, we have all of our outcomes listed here. And then in order to get the actual probabilities, what we do is we take the number of occurrences. So for example, the 1344, and we divide it by the total, which was 3939. And we get 0.341. Side with dot, we get 0.329, and so on, all the way down. So we've created our probability model. And if you look at it, just to confirm it's a probability model, if we add all of these up, we should get 1. And if we look at all of them individually, they're somewhere between 0 and 1. So that means that it's a valid probability model. The probability a throw results in a side with dot is 0.329. We could also say that that means that out of 1,000 throws of the pig, we would expect about 329 of them to land on side with dot. Or we could say that we have a 32.9% chance. A leaning jowler would be unusual, okay? It only happens about 0.8% of the time. So if we look at 1,000 throws, you're only going to get that about 8 times. So that's pretty unusual. Now, the classical method of computing probabilities requires equally likely outcomes. So an experiment is said to have equally likely outcomes when each simple event has the same probability of occurring. So if we look at this formula here, if an experiment has n equally likely outcomes, and if the number of ways that an event E can occur is m, then the probability of E, or P of E, is denoted as follows. We take the number of ways E can occur, which is M, and the total number of possible outcomes, which is N, and we divide. So if S is our sample space in this experiment, then really all we need to do is we take the number of events, the number of outcomes in E and the number of outcomes in our sample space, and we just divide those two things. So let's suppose that a fun-sized bag of M&Ms contains 9 brown candies, 6 yellow candies, 7 red, 4 orange, 2 blue, and 2 green. And we want to suppose that a candy is randomly selected. So, for example, you still have your M&Ms in your actual bag, and you have already counted, and these are the color M&Ms that you have. So if we want to know what is the probability that we choose a yellow, that means that we would take 6, which is the number of yellow that we have, and divide it by 30, which is the number of total M&Ms that we have. So if we do 6 over 30, we get 0.2, or you could say 20%. Probability that we get a blue, there are only 2 blues, so we take 2 over 30, and we get 0.067, or 6.7%. So it's less likely than yellow. Let's see. Comment on the likelihood of the candy being yellow versus blue. So this is just comparing the two. So selecting a yellow is actually 3 times as likely as selecting a blue. And if we look back at our numbers, we have 6 yellows and 2 blues. So we have 3 times as many yellows than blues. Okay, section 5.2, we're going to talk about the addition rule and something called complements. So 2 events are considered disjoint if they have no outcomes in common. Another name for disjoint events is mutually exclusive events. So it means that there is no outcome that's in common. So often we draw pictures of events using Venn diagrams. They allow you to see situations visually, and the pictures represent events as circles enclosed in a rectangle. The rectangle is your sample space, and then each circle is an event that we're interested in. So for example, let's suppose we randomly select a chip from a bag where each chip in the bag is labeled 0 through 9, all of the integers. We're going to let one event represent the fact that we choose a number less than or equal to 2. So that would be this purple event here, where we get a 0, a 1, or a 2. F is going to represent the event where we choose a number greater than or equal to 8, which would mean that we choose an 8 or a 9. Those 2 events are disjoint, so there's no overlap between the 2. And then you'll see that the 3, 4, 5, 6, 7, they live in this outer blue part because they don't belong in either of the events. So if we look at our 2 disjoint events, if we want to find the probability of E, okay, so the probability of selecting a number less than or equal to 2, then we take the number of outcomes in E, which is going to be 3 here if we count 1, 2, 3, divided by 10, which is the total number in our sample space. So 3 over 10, or 0.3, or 30%. The probability of getting F, which means that the probability of choosing a number that's greater than or equal to 8 is going to be 2, because we only have 2 numbers that are greater than or equal to 8, divided by 10, which is our total. So we get 0.2, or 20%. The probability of getting E or F, basically we look at E, we look at F, and we put them together. So we're happy with getting either, so that means we're happy with 1, 2, 3, 4, 5 different outcomes out of our 10, so we get 0.5, or 50%. And if you look at this calculation, we could look at probability of E, which was 0.3, probability of F, which was 0.2, and if we add them together, we get the exact same thing, which is really our addition rule for disjoint events. So if E and F are disjoint, or we could call them mutually exclusive, then the probability of E or F happening is just going to be the probability of E plus the probability of F. So when you see OR problems, they're going to go with addition. So it can be extended to more than 2 disjoint events. That's one kind of important thing. So if you have E, F, G, and so on events, and each have no outcomes in common, meaning they are pairwise disjoint, then in order to find that probability, you just continue to add up those events. Okay, so the probability model to the right shows the distribution of the number of rooms in housing units in the US. We want to verify first that it's a probability model. And it is because all of the numbers are between 0 and 1, and if we add them all up, we get 1. What is the probability a randomly selected housing unit has 2 or 3 rooms? So what you need to do is you need to find the probability of getting 2 or 3. So you take the probability of getting 2 and add it to the probability of getting 3. You can't have a house that has 2 rooms and 3 rooms, okay? You either classify it as one or the other. So in this case, we need to add those two things together because we have disjoint things. So it's going to be 0.032 and 0.093. We add them up and we get 0.125. About a 12.5% chance of choosing a randomly selected house that has either 2 or 3 rooms. What is the probability a randomly selected house has 1 or 2 or 3 rooms? So this is pretty much the exact same thing, except we have 1 in there as well. So we have to add that as well. If you add them all up, you get 0.135 or 13.5% chance. Okay, so that was our addition rule when we have disjoint events. We also have a general addition rule, okay, and this works for disjoint events or events that are not disjoint. So for any two events, E and F, the probability of getting E or F, it starts out the same way. It starts out as probability of E plus probability of F. However, what you need to do is when you have two events that are not disjoint, you need to subtract the overlap so that it is not counted twice in your actual equation. So if we look at this, let's suppose that a pair of dice are thrown. Let's let event E be equal to the first die is a 2, and we're going to let event F equal the sum of the dice is less than or equal to 5. We want to find the probability of E or F using the general addition rule. So the probability of E happening, meaning that the first die is a 2, if we look at our table here, this whole row right here all has pairs where the first die that was rolled is a 2. So if you look at the number of pairs, we have 1, 2, 3, 4, 5, 6 out of our 36 total pairs. So 6 out of 36, which is just 1 out of 6. Excuse me. So sorry about that. Now the probability of F, meaning that we're finding the probability that the sum of the dice is less than or equal to 5. If we look at it, let's see, we have this observation here, this one, this one, this one, this, and then this diagonal, 1, 2, and 3 more. So we get a total of 10. It really is just this little corner here, all right, out of our 36, which reduces to 5 over 18. And then what we want to find is we want to find the overlap. So what we're looking for is we're looking for things that fit into both groups. So which ones did we select twice? So we're looking for ones where the first die is a 2 and the sum of the dice is less than or equal to 5. And if you actually look at it, these three observations right here, 2, 1, 2, 2, 2, 3, they all have 2s as their first die. And the sum of all of them is, or if each of them is less than or equal to 5. So there are 3 observations that are in our overlap. 3 out of 36 or 1 out of 12. So what we need to do is we need to add the first 2, probability of E plus probability of F, and then subtract that overlap so that it's not counted twice. And it's normally easiest to use your not reduced fractions because they should all have the same denominator at this point. So you should get 13 out of 36, which does not reduce. The whole idea behind subtracting this overlap is that we don't want to count the same observations twice. It wouldn't be fair. So if we look at the ones that have the first die of 2 and the sum of the dice less than or equal to 5, then that allows us to find these 3 pairs that we counted in both sets so that we subtract it from 1 so that we don't include it both times. Okay, the next thing we're going to talk about is the complement of an event. So let's let S denote the sample space of a probability experiment and let E denote an event. The complement of E, which is denoted EC, with the C as kind of an exponent, is all outcomes in the sample space S that are not outcomes in the event E. So here's our nice little complement rule. If E represents any event, then E of C represents the complement of E. So we say that the probability of E complement is equal to 1 minus the probability of E. So if you think about it, we have E, that's our event, and we have E complement, which is everything that is outside of our event. So the entire region, and then we have the area outside of the circle, is going to represent E complement. So according to the American Veterinary Medical Association, 31.6% of American households own a dog. What is the probability that a randomly selected household does not own a dog? So these are very helpful when you have not type questions. So all you have to do is take 1 minus the probability that they do own a dog. Because if you think about it, if you think about the possible outcomes, they either own a dog or don't own a dog. Those are the only two outcomes. So we take 1 minus 0.316 and we get 0.684. So that means we have a 68.4% chance of randomly selecting someone who does not own a dog and a 31.6% chance of randomly selecting a household who does own a dog. Okay, the data to the right represents the travel time to work for residents of Hartford County, Connecticut. What is the probability a randomly selected resident has a travel time of 90 or more minutes? So if we look at this, there are a total of 393,186 residents if we add all of these up. And then the probability that a randomly selected resident will have a commute time of 90 or more minutes is going to be 4,895 out of the 393,000. Which is just 0.012 or 1.2%. Now we want to compute the probability that a randomly selected resident of Hartford County will have a commute time less than 90 minutes. Since we know the percent that have a commute time more than 90 minutes, all we have to do is take 1 minus our previous answer. So we take 1 minus our 0.012, which is 0.988 or 98.8%. Okay, section 5.3 is about independence and the multiplication rule. So two events E and F are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. Two events are dependent if the occurrence of event E in a probability experiment affects the probability of event F. So let's suppose you draw a card from a standard 52 card deck and you also roll a die. The events draw a heart and roll an even number are independent because the results of choosing a card have absolutely no impact on the results of the die toss. So let's suppose that two 40-year-old women who live in the US are randomly selected. The events woman 1 survives the year and woman 2 survives the year are independent because they have nothing to do with one another. But now let's suppose that two 40-year-old women live in the same apartment complex. The events women 1 survives the year and women 2 survives the year are actually going to be dependent because it's possible that one affects the other. Okay, so the multiplication rule for independent events is given as follows. If E and F are independent events, then the probability of E and F happening are going to be the probability of E times the probability of F. So we have a few rules so far. So when you have or type questions, you add and you need to subtract the overlap. When you have not type questions, you need to do 1 minus. And when you have and type questions, you're going to be multiplying. So the probability that a randomly selected female aged 60 years old will survive the year is 99.186% according to the National Vital Statistics Report. What is the probability that two randomly selected 60-year-old females will survive the year? So the survival of the first is going to be, or the probability for survival of the first is going to be 0.99186, and the probability of survival for the second is going to be the same. So all we have to do is we need to multiply that number by itself. The other way you can think about this is you could do it as 0.99186 squared, and you get 0.9838. You could also do this with more observations. What's the probability that 10 randomly selected 60-year-old females will survive the year? You could take 0.99186 and raise it to the 10th power. Okay, a manufacturer of exercise equipment knows that 10% of their products are defective. They also know that only 30% of their customers will actually use the equipment in the first year after it is purchased. If there is a 1-year warranty on the equipment, what proportion of the customers will actually make a valid warranty claim? So we assume that the defectiveness of the equipment is independent of the use of the equipment. So probability defective and used is going to be the probability that it's defective, which is 0.1, and the probability that it's used, which is 0.3. And then if we multiply them, we get 0.03 or 3%. So that means that of the people who purchase the 1-year warranty, probably about 3% will make a valid warranty claim. We can also have more than just 2 events. So the previous examples that we looked at only had 2 events, but if we have more than 2 and they're all independent, then we just multiply all of them. So the probability that a randomly selected female aged 60 years and older will survive the year is 99.186, which we already talked about. What is the probability that 4 randomly selected 60-year-old females will survive the year? So what we do is we take probability that the first survives, second, third, and fourth, and multiply them. So it's going to be 0.99186 times 0.99186 4 times, or an easier way of doing that would be to take 0.99186 in your calculator and raise it to the 4th power, and you get 0.9678. Okay, there are also at least type probabilities. So the probability that a randomly selected female aged 60 years old will survive the year is 99.186. What is the probability that at least one of 500 randomly selected 60-year-old females will die during the course of the year? So the probability that at least one dies is going to be 1 minus the probability that none die at all. Because if you think about it, our options are that everyone lives, meaning that none die, or at least one dies. So we take 1 minus the probability that all of the people survive, which is going to be 1 minus 0.99186 raised to the 500th power, since we have 500 people, and you get 0.9832. So there's about a 98% chance that at least one of 500 randomly selected 60-year-old females will die during the course of the year. Now that means one female could die, or 2, or 3, or 4, and so on. Okay, section 5.4 deals with conditional probability and a general multiplication rule. So let's look at this notation here. The notation probability of F given E. Okay, so you read this line as the word given. So probability of event F given E is just the probability that event F is going to occur given that event E has already occurred. So it's like you already know the future. You know event E has occurred. Now what's the probability of event F occurring? So let's suppose that a single 6-sided die is rolled. What is the probability that the die comes up with 4? Now suppose that the die is rolled a second time, but we are told that the outcome will be an even number. Now what is the probability that the die comes up for? So if we think about our first roll, the probability of getting a 4 is just 1 out of 6 because we have one number 4 out of our 6 total numbers. But with our second roll, we had kind of like a magic ball that told us, okay, you're going to be getting an even number, I know it. So that means that your sample space are just the even numbers, 2, 4, and 6. So the probability of getting a 4 is now 1 out of your 3 possible outcomes. So it's 1 out of 3. Now we do have this conditional probability rule that allows us to kind of think about this in a more abstract concept or context when we don't have something that we can just look at like that somewhere where we can't necessarily list the entire sample space. So if E and F are any 2 events, then the probability of F given E can be found by taking the probability of E and F happening and dividing it by the probability of E. So you take probability of E and F and divide it by probability of E. So a survey was conducted by the Gallup organization in May of 2008, in which about 1,000 adult Americans were asked the following question. Which of the following statements comes closest to your belief about God? You believe in God, you don't believe in God, but you do believe in a universal spirit or higher power, or you don't believe in either. The results of the survey by region of the country are given in the table on the next slide. So we have East, Midwest, South, and West. Believe in God, believe in universal spirit, and don't believe in either. So what we'd like to find is the probability that a randomly selected adult American who lives in the East believes in God. So we have probability that they believe in God given that they live in the East. So we take the number of people who believe in God and live in the East, which is going to be this 204, and we divide it by all of the people who live in the East, 204 plus 36 plus 15. And make sure if you're doing this in your calculator all at once that you put parentheses around your denominator, and you get 0.8. So that means if you know that someone lives in the East, there's about an 80% chance that you're going to choose someone who believes in God out of this group of people. So now let's do the probability that they live in the East, given that they believe in God. So that means that we want the number of people who, again, believe in God and live in the East, but this time we're just looking at the people who actually believe in God. So we take our 204 again, and then we divide it by the total number of people who believe in God, which is going to be the 204, the 212, and so on. And we get 0.26. So that means that out of this group of people, if we know that we've chosen someone who believes in God, there's about a 26% chance that they live in the East. Okay, let's look at this murder victims example. So in 2005, 19.1% of all murder victims were between the ages of 20 and 24. Also in 2005, 16.6% of all murder victims were 20 to 24-year-old males. What is the probability that a randomly selected murder victim in 2005 was male, given that the victim is 20 to 24? So if we look at this, what we're trying to find is the probability that the person is male, given that they're 20 to 24. So I want you to use this formula here. We take the and, okay, so the probability that they're male and 20 to 24, and we divide it by the probability that it's just someone who's 20 to 24. So I want you to take a minute, plug in the numbers that we have for those, and see what you guys get. So I'm going to give you about 30 seconds to go ahead and do that. Okay, so if you've calculated that, you should get the 0.166 and divide it by the 0.191, and you get 0.869 or 86.9%. So that means that the probability that a randomly selected murder victim was male, given that they were 20 to 24, is almost 86%, or 87. Sorry, almost 87%. Okay, now we have this general multiplication rule here. So the probability that two events E and F both occur is given by probability of E and F equals probability of E times the probability of F given E. So in other words, the probability of E and F is the probability of an event E occurring multiplied by the probability of F occurring given that E already occurred. So this is slightly confusing to think about. Once you've used it a few times, you'll get used to it. But let's look back at our murder victim example. And let's say that we want to find the probability that we selected someone who is male and 20 to 24, if we're selecting a murder victim. So what we do is we take the probability that we select someone who's 20 to 24, and we multiply by the probability that they're male given that they're 20 to 24. This is really just a rearrangement of the previous example. So the 20 to 24-year-olds is going to be the 0.86, or sorry, the male given 20 to 24 is going to be the 0.869, and the probability of choosing someone who's 20 to 24 is the 0.191. These two are kind of flip-flopped. It's multiplication, so it doesn't matter. And you get 0.1659, or about 16.6%. So the probability that a randomly selected murder victim in 2005 was a 20 to 24-year-old male is going to be about 16.6%. Okay, section 5.5 is a little different. We talk about counting techniques. So there's a multiplication rule of counting. So if a task consists of a sequence of choices in which there are P selections for the first choice, Q selections for the second choice, and R selections for the third choice, and so on, then the task of making these selections can be done by multiplying P, Q, and R. That's going to give you the number of different ways in which the selections can be made. So the easiest thing to think about is food, okay? So if we talk about choosing an appetizer, an entree, and a dessert. So let's say, for example, that for a choice of an appetizer, we have 4 choices. Or actually, no, it looks like we have 2 choices for an appetizer, 4 choices for an entree, and then 2 choices for dessert. So what you do in order to get that, the total number of different meals that you can make, is you take your 2 appetizers, your 4 entrees, and your 2 desserts, and you just multiply, and you get 16 different meals that can actually be ordered. If n is greater than or equal to 0, is an integer, the factorial symbol, n factorial, is defined as follows. So it's n with, it's literally just an exclamation point, okay, but we read it as factorial in math. So n factorial is just found by taking n and multiplying by n minus 1, n minus 2, and so on, all the way until you get to 3, 2, 1, or whatever. A couple of quick rules. 0 factorial is actually 1, and your calculator will give you this if you plug it in, and 1 factorial is also equal to 1. Now, a permutation is just an ordered arrangement in which R objects are chosen from n different objects, and repetition is not allowed. So the symbol NPR represents the number of permutations of R objects selected from n objects. And there's a formula here. This is not something I would memorize, because your scientific or graphing calculator will do this for you. Oftentimes, if you can't figure out how to do it, you can Google it. But if you have a scientific calculator, most likely it lives under a button called PRB. And if you have a graphing calculator, I think it lives under STAT. I am not totally sure about that, though. So the number of permutations of n distinct objects taken r at a time can be found by taking n factorial and dividing by n minus r factorial. So this is the typical formula, but you do not need to use this, because what you can do is you can use your NPR button in your calculator. So at this point, if you don't have a calculator, pause the video and go grab one. Okay, now that you're back, so we want to know, in how many ways can horses in a 10-horse race finish first, second, and third? Excuse me. So the 10 horses are distinct, and once a horse crosses the finish line, that horse cannot cross the finish line again. And if we're talking about a race, order is important, because first place is different than third place. So we have a permutation of 10 objects taken 3 at a time. So the top 3 horses can finish a 10-horse race in 10 pick 3 ways. I normally like to read permutations as the word pick, just so it makes a little more sense. So out of our 10 horses, we're picking 3 of them to win. Now, I don't want you to do this by hand, okay? It's not necessary. What I want you to do is I want you to hit the number 10 in your calculator, and then if you have a scientific calculator, hit PRB, and then find where it says NPR, hit equals, and then hit 3, and then equals again, and you should get 720. If you have a graphing calculator, I don't recall off the top of my head exactly where it lives, but it's the same idea. You hit 10, and then if you find your NPR button, you hit that, enter 3, and then enter, and you also get 720. Now, a combination kind of goes with the permutation, except it's a little bit different. Combinations, the order doesn't matter. Okay, so for permutations, the order matters. For combinations, the order does not. So we have a slightly different algebraic formula here, but again, if you're using your calculator, which I would highly recommend, you don't need to actually use that. So how many different simple random samples of size 4 can be obtained from a population whose size is 20? So the 20 individuals in the population are going to be distinct, but the order doesn't actually matter. So if you're chosen for the simple random sample, it doesn't matter if you're chosen first or fourth, you're still being chosen. So the number of simple random samples of size 4 from a population of size 20 is going to be a combination of 20 objects taken 4 at a time. So again, I would not recommend doing this the long way. But if you look at it, out of 20 objects or 20 people, we're choosing 4 of them. So I like to read permutations as pick and combinations as choose when I'm reading them kind of in my own head. So this is out of 20, we choose 4. Again, in your calculator, you're going to hit the 20. You're going to hit your NPR button if you have it, or sorry, your PRB button if you have it. Scroll over to where you have NCR instead of NPR, hit enter, and then hit 4 and enter again. And it's going to be pretty much the same thing, but you get 4,845. It's a slightly different calculation, so it's calculated a little differently, and that's just based on whether or not the order matters. So there are 4,845 different simple random samples of size 4 from a population whose size is 20. We can also have permutations with non-distinct items. And if we have that, what we do is we take n factorial, where n is the number of objects, and we divide it by all of the duplicate objects. So if we look at this, for example, arranging flags is a really typical example of this. Also arranging letters in a word or arranging numbers in a phone number. So how many different vertical arrangements are there of 10 flags if 5 are white, 3 are blue, and 2 are red? So let's just think about our 2 red flags for a minute. Assuming that they're identical, which that's kind of the assumption we need to work under, if we flip-flop our 2 red flags, nothing has actually changed. But if we flip-flop our red and our blue flags, then the pattern is going to look different. So the order does matter, but with the 2 red flags or the 3 blue or the 5 white, it doesn't matter if we flip those within those groups because it's going to look the same. So that's why we have to use this kind of special formula that accounts for that. So in order to do that, we take 10 factorial because that's the total number of flags we have, and we divide by our duplicates with factorials attached. So for example, we have 5 factorial because we have 5 duplicate white flags, 3 factorial for our 3 duplicate blue, and 2 factorial for our 2 duplicate red. And then all we have to do is just use our calculator. You should have a factorial button in that same kind of location right by NCR and NPR. So you can use that. Make sure when you divide, you put parentheses around your denominator. And that will give you an answer of 2,520 different vertical arrangements. Okay, let's look at this example here. In the Illinois lottery, an urn contains balls numbered 1 to 52. From this urn, 6 balls are randomly chosen without replacement. So for a $1 bet, a player chooses 2 sets of 6 numbers. To win, all 6 numbers have to match those chosen from the urn. The order in which the balls are selected does not matter, and we want to know what is the probability of winning the lottery. So, if you think about this for a minute, the probability of winning is given by the number of ways a ticket could win divided by the number of objects or events in our sample space. So outcomes in our sample space. Each ticket has 2 sets of 6 numbers, so there are 2 chances of winning for each ticket. Now the sample space S is going to be the number of ways that 6 objects can be selected from 52. Now what they told us is that this is the order does not matter, so that means it's going to be a combination. So out of our 52 balls, we choose 6 of them. So the number of objects in our sample space, again, do not do this by hand, just type in your calculator 52C6. You get 20,358,520. Now each ticket has 2 sets of 6 numbers, so if a player has 2 chances of winning for each $1, if the event E is a winning ticket. So we would take their 2 chances and divide them by the 20 million, and you get 0.00000098 as your probability of winning. So very, very, very small. The more tickets you buy, the larger your numerator is going to get, so the larger that this number gets. So that's about a 1 in 10 million chance of winning the Illinois lottery. So very, very small. That's for 1 ticket. Again, if you buy 2 tickets, you'd have a 2 in 10 million chance. If you buy 10 tickets, you'd have a 10 in 10 million chance or a 1 in a million chance. But that's it for this week. Thank you for listening. I don't think there's anyone logged on. No, there's not, so there won't be any questions.